Hi, welcome back. So in this video we're going to be talking about trig substitution, so particularly part A of our trig substitution week. So this section is super intimidating. Don't be scared. We're going to spend a lot of time kind of breaking down the steps, and eventually you'll see it's all kind of the same steps every time. It just kind of looks intense. Okay, so what we're going to do in this video is make a chart out of what the hell is going on, at least for all the beginning steps. What we're not going to talk about today is what those triangles are in the book. The triangles are what we'll pick up with next class. Okay, so here's the general idea. When you see one of these three types of things in your integrand, you are going to make a substitution as prescribed in the book. Okay, so if you see the square root of something minus x squared, the only reason we say a squared here is so that we can say a here. So if this is 4, you choose a 2 over here. If this is 10, you put square root of 10 over here, right? So this is just the square root of whatever number is there. All right, so if you see that, then you plug in x equals that number times sine of theta. So this theta right here is a new variable. It's sort of like the u in u substitution. What's different from what we're doing to u substitution is that instead of like new variable equals a function of x, we have x equals function of new variable. But generally substitution works the same way after that. It's just kind of a perspective thing. Okay, so if you choose that as your substitution, remember a is just a fixed number. It'll be like a 2 or something. That means that your dx would be a cosine theta d theta, because that's just the derivative of the above. And then you also have this range, right? So they say for theta in minus pi over 2 to positive pi over 2, which is essentially the right half of the unit circle. Don't stress this just yet. We'll talk about this I think in class after this video, so we're not gonna stress that today. No, maybe we should. Yeah, we will. I'll talk about it. We'll talk about it. Okay, so you don't have to memorize it at least, right? Because you can always use your notes. But really, this is telling us the right half of the unit circle, and it also happens to be the range of arcsine. That's really why it's here, right? Okay. So if you sub that in, then you are going to simplify your integrand. So you plug everything in. And then you have a few simplifying steps, right? Because when you plug all this stuff into your integrand, it's going to look horrible for a minute. But then through the magic of trig identities, it kind of works out. All right, so you would simplify using 1 minus sine squared. I'm just screw this up. 1 minus sine squared of theta equals cosine squared theta. So when you put a sine in for x into this expression, you'll get a squared minus a squared sine squared. Factor out the a squared. I should actually include that here. Let's kind of add it as a step here. That a squared will get factored out in that step. So you'll end up with 1 minus sine squared, and you'll say, I happen to know that that is cosine squared. All right, so this is actually where the range is coming in, so we should talk about it. So another identity that may come into play, and it does often, it just won't anytime the square root isn't there. I have a note here, that root may not actually be there, and this all still works, but then you wouldn't use this last column. So what you'll end up with is the square root of cosine squared, right? So you'll put this substitution, so you'll get cosine squared under that root. So the square root of something squared it doesn't perfectly cancel. It would wipe out a minus sign if it were there. So we can't just say cosine, we'll say the absolute value of cosine. But if theta is between minus pi over 2 and positive pi over 2, we're talking about from here to here. The cosine of theta is the x value. And for every single one of these points, their x value is positive, right? Because all the negative x's are over here. So the absolute value of cosine in this magical range actually is equal to plain cosine, which is going to end up making your integrand obviously way nicer to work with. So You can do this only because of the restriction that was on theta to begin with, and that restriction is there because it's the range of arcsine, but don't stress that part. Okay, so when you see this thing, you're going to make this substitution, and there's a lot of work involved here. You're going to compute your derivative, actually plug stuff in, factor out that a squared, use this trig identity to simplify, and then probably this one to simplify a little more. All right, so I'm going to fill in the rest of this chart, and then this video will end with an example. So if this isn't all, so crystal clear immediately, we will actually use it in a minute. Okay, so the other two possibilities are a squared plus x squared. You may or may not see this root, but we include it in the chart because it's usually there. All right, so the substitution you would make is for a tan theta. And again, a is just, whatever number is the square root of what you see here. So that would make the dx a secant squared theta, because that's the derivative of tangent theta. And then we'll say for theta in the range of arctan, which is minus pi over 2 to positive pi over 2. But we use parentheses instead of brackets because now they're not included because arctan doesn't exist there. Okay, so the Pythagorean identity that has tangent in it is 1 plus tangent squared equals secant squared. Right, so that's the identity you would use, right? So you still factor out that a squared, that step carries for all of them. So you'll end up with 1 plus tan squared. You'll say, that's secant squared. And then look, you've got square root of secant squared. And that brings us to this last column, where technically this should be the absolute value of secant, which is really going to complicate the integral. But we'll realize we're still on the right-hand side of the unit circle, just not including those edges. And if the cosine is positive there, the secant is just 1 over cosine. The secant's always positive, so we really can just call that regular secant, and that's going to help us simplify our integrand. All right, so the very last one is kind of the messiest, but we'll kind of make some assumptions to keep it cleaner. So the last one is root of x squared minus a squared. Again, that root may not be there, but that's fine. The substitution you'll make is for square root of this number times secant theta. That would make your dx a secant tangent, because that's the derivative of secant. And this one's a little extra messy. The book has some more details, so I'll kind of put a star here, kind of an asterisk for, seek more details in the book. But we're going to say for theta in 0 to pi over 2, just kind of the first half of the two pieces that we really could have for arc secant. It kind of has two chunks for its main domain, or sorry, range. Anywho, so we'll stick with that, and we're kind of assuming that I think it's x is greater than or equal to a, and it's not something that you'll have to stress when you do these problems. Okay, so in this case, you would have a squared secant squared right here minus a squared. Factor out your a squared, so you have secant squared minus 1. And there's an identity. Really all I'm doing is rearranging this identity, right? Subtract the 1 onto this side, and we've got secant squared minus 1 is tangent squared. But this is how you'll see it show up. And then, of course, as long as we're in making these extra assumptions, the square root of, oh no wait, it should be a square root of tangent squared. Ignore that. The square root of tangent squared theta, really that's the absolute value of tangent, but as long as we are in the first quadrant, which is what this is here, your tangent is positive. So we can just say regular tangent, and that makes our integrating that much easier. So before we jump into the example, I want to point out these identities here absolutely get used every time, this column. These identities are why you're choosing these substitutions, right? So we choose a sign when we have a number minus x squared, because we know that we can turn this into 1 minus, in this case, sine squared. We go, oh, I have an identity for that. right? And then here we know we can get it to be 1 plus tangent squared. We have an identity for that. And then same thing here, x squared minus 1, we would have an identity for. So these identities are kind of the whole point. So you may not always use this confusing column, but you should always use this one because it's a big part of the plan. All right, so let's take a minute or two. We're not going to get to totally finish this example because there's more to talk about next class, but we'll at least kind of get started on the first few steps. So I have the integral of the root of 1 minus x squared. This is actually a really tough integral. So this is going to fit the first row of my chart here. So when I see this, that's what I see here, where the a is 1. So this one, a squared and a just are 1. Plug in this. Okay, so I'm going to choose x equals 1 sine theta. And again, this is the only case where these two numbers would be the same. If this was a 4, I would choose a 2 here. Okay, so now I'm going to compute the dx. So that would mean dx equals cosine theta d theta. And then I'll remind myself about that range of theta. Don't stress memorizing it, remember, because you can always have these charts in front of you. Anytime you do the sign substitution, this will be the range for theta. Okay, so then we'll plug stuff in. In this one, we only see x in that one spot, but you will see more where they're like more complicated and this gets substituted into more than one place. But we'll get to those later. All right, so here we have 1 minus sine squared theta. That's my x squared. And then dx is cosine theta d theta. All right, so in this one that factor out the a squared, we're going to skip that step because a was just 1. If a squared had had been, let's say, 4, we would now have a step here where we factor out a 4, but we don't have that here. So we're going to jump straight to the simplify with this. So I have 1 minus sine squared. I'm going to put cosine squared under that radical instead. And then we have cosine theta d theta from the dx here. All right, and then we are going to use that final column here. For this particular range of theta, the square root of cosine squared is just cosine. So I'm going to kind of make a note to myself. This isn't always the case, but here it is. All right, so what I have is a cosine here times another cosine here. So I'm actually integrating just cosine squared theta d theta. Whew. Okay, so this is not an easy integral, but it is one of the integrals that's in your resources folder. So there's a document, and I think they're called reference materials folder. So it's called useful trig integrals, and I have just a whole bunch of trig integrals that might be helpful. You'll see cosine squared is right here. So you have access to this in your notes. All right, so cosine squared, we're not going to bother. Really, you do this with integration by parts in a cool wraparound way, the same way that e to the x cosine of x happens. So we have 1/2. Here my variable is theta plus sine theta cosine theta plus c. All right, so that's right off my sheet of useful trig integrals from the reference materials folder. All right, and now we've actually integrated, right? This step right here, that was actually the goal, right? This is what we're trying to do, is integrate. So our last step is to switch back into x's. And we know that x equals sine theta, right? So right here, we say, okay, that's definitely x. If I solve this for theta, I would get that theta is the arc sine of x. Just kind of rewrite it as an inverse. So that theta we could write as arc sine of x. But then, what the heck are we supposed to do with cosine of theta? So this is the part where the triangle comes in, and that's something that we'll wait to talk about until next class. So hold off on that. There would just be one extra step before the final answer here.